If you recall, yesterday we had an exercise on continuity. We want to identify where a function was discontinuous and where a function was not differentiable. And we want to be able to explain why the function was discontinuous or not differentiable at those points. Remember our requirements for continuity. There are three things. We need the limits as x approaches c of f of x to equal f of c. And this means three things. One, the function is defined. Two, the limit exists. Or three, if those two are in play, then we can call on the third one, make sure that those things are the same. So a function f is continuous at c if limit as x approaches c of f of x equals f of c. That contains three things. The exercise yesterday was to identify where a function was not differentiable and then explain why. First, by just identifying 1, 2, or 3. What was the problem? 1, 2, or 3? And then explaining why 1, 2, or 3 did not hold at those particular points. So if you would recall, this was our graph. I just want to be clear, make sure that we're all writing things properly. Remember, math is a very pedantic language and it's very precise. And so we want to make sure that we communicate things properly. So where was this function discontinuous? What values of x was the function discontinuous? The function was discontinuous at 1, 2, 3, and 4, but not 5 and 6. 5 and 6, what was going wrong at 5 and 6? It's not differentiable because of the pointy bits. Where else is it not differentiable? 1, 2, 3, and 4. Good. So differentiability implies continuity. Differentiability is a stronger condition. First, you get the continuity, then you get the differentiability, then you get the power. Wait, no, that's Scarface. Scratch that last bit. So at 1, 2, 3, and 4, the function is discontinuous. So f is discontinuous at x equals 1, 2, 3, and 4. F is discontinuous at 1, 2, 3, and 4. What reason could we give for f of x being discontinuous at 1? Which of these three things does not hold? Which of the three conditions doesn't hold at 1? Kind of all of them. The function is not defined. We see the vertical asymptote. There's no value f of 1. So first, 1, f of 1 is undefined. What else is wrong? There's no limit. The function does not have a limit. We're not approaching any value. From the left, the function is headed to infinity, not a value. From the right, the function is headed towards negative infinity, also not a value. The limit just doesn't exist. One thing that we want to point out here is that when we talk about does not exist, right now, we only get to apply that to limits. Does not exist semantically is different than undefined. The limit does not exist. The function is undefined. So DNE, does not exist, is language that we're going to use for limits. Undefined is what we're going to use for the values of the function. The third one doesn't really enter into it. These things can't be equal because there's no value for the limit to equal. And there's no value that the limit is. So that third one doesn't really enter into the discussion. Great. What happens? So as you notice, 1 through 4, things just kind of escalate. Things just kind of like, actually, this is, I guess, de-escalate, because this is like the worst case scenario. No value, and we can't even say where the function is headed because it's doing one of these. What's happening at x equals 2? What's wrong at x equals 2? F of 2 is undefined. There's no value. When we try to look up the value of the function, f of 2 is undefined. Oops. There is no value that we can assign to the function when x is equal to 2. What about the limits? Does the limit exist? Yeah, the limit exists, but that's not relevant because the limit is, the function is headed somewhere, but the function is nowhere when we get there. So we can say that 2 is okay. The limit as x approaches 2 of f of x is equal to -1. But that first one, the function being undefined, means the function is discontinuous. The third one doesn't really apply since the function is not defined. There's nothing to make the comparison. There's nothing to put in the equation. So in the first one, I guess we could say f of 1 is undefined, and in the second one, f of 2 is undefined. I should actually say it this way. The limit as x approaches 2 of f of x equals -1, but f of 2 is undefined. What's going on at 3? Oh, in case you forgot. In case you don't have photographic memory of what a graph looks like. What's going on at 3? Is the function defined? Is f of 3 defined? What is f of 3? 0. So first, f of 3 is defined. F of 3 is equal to 0. But what's wrong? The limit doesn't exist. The function is defined, but the limit doesn't exist. Now, let's suppose that we were pressed on this issue. Why does the limit not exist? We're sitting in front of Judge Judy, and she's like, well, how do you know the limit doesn't exist? I can't do a Judge Judy impression, so just live with it. The values that we're approaching from the left are different than those that we're approaching from the right. What are we approaching from the left? So if we needed to explain why this limit doesn't exist, we could say that the limit as x approaches 3 from the left, what are we headed towards from the left? 0. And what is the limit as x approaches 3 from the right? Looks like we're headed towards 3. Looks like a little less than 3, but let's just call it 3. And these two values are not the same. If we have values that we can work with, we should use those values as a cite. We should cite those values. Rather than just saying the limits are, the one-sided limits are not equal, state what the one-sided limits are. Because that's your evidence. So the one-sided limits are unequal. That's part of our evidence. So we also said the function was discontinuous at x equals 4. What's wrong at x equals 4? The limits doesn't equal the value of the function. So we have, the function is defined. So number one, the function is defined. So that's okay. What is f of 4? 2. It looks like the function is equal to, oops. I switched them up. I did exactly backwards. The value of the function is equal to, I also put the wrong thing. Okay, write a f of 4. So what is f of 4 equal to? Oh, it's not up there. It's down here. Third time. Am I right now? Okay, I'm a little concerned because I'm clearly not seeing things clearly. So the function is defined. F of 4 is equal to -2. When your function is defined, rather than saying the function is defined, prove that you recognize that the function is defined by saying f of 4 is equal to -2. That's enough to say that the function is defined. And what's the limit as x approaches 4 of f of x? 2. We can see that on the graph. From the left, we're going to 2. From the right, we're going to 2. So the limit is 2. But what's wrong? As you stated earlier, the value of the limit is not the value of the function. Any questions? How's everybody okay? In the discussion version, in the discussion that's attached to this, the in-class exercise yesterday, you have a few options for when it comes to writing your explanations for things. So I think in the discussion, I just said, just name 1, 2, or 3, which one of those three things is bad. If you want to write an explanation for that, you're gonna have to find a way to express the limit parts. So at this point, for say, let's say for x equals 3, if you wanted to write an explanation, you could just use the words. The limit as x approaches 3 from the left is 0, but the limit as x approaches 3 from the right is 3. So the one-sided limits are unequal. Therefore, the limit doesn't exist. You could just use those words. The symbols are to help us write things. So the symbols are so we can abbreviate when we're writing things, because that's tiring. So we have now adapted our machines to allow us to type things like this. So we have an exercise coming up. I guess today. We have an exercise coming up that will be having you practice typing things using the equation editor that goes on with Canvas. But for the purposes of the discussion, you don't need to do equation editor unless you want to show off your mad LaTeX skills. Right now, you can just use words. Any questions? How's everybody, okay? So as far as the second part of the question goes, I did ask about not where, secret question. I did ask about non-differential, where the function is not differentiable. The function, if the function is discontinuous at a point, the function is not differentiable at a point. We can't put a tangent there. If there's a hole in the graph, there's nowhere to put a tangent. There's nowhere to attach the tangent. The tangent just goes sliding through the point, then it tilts and then falls out. So nowhere to put it. There's nowhere to put a tangent at the point 1 because there's no point to attach it to. Also, there's no point to attach it to here. Where do I attach the tangent at 3? Down here, up here, what? Also, there's nowhere to put it on 3. If I try to balance it on 3, then it would just fall off to the side because it would be unbalanced. At 4, down here is where the value of the function is, but there's no direction for the function. It's a little bit on the nose. I know where I'm at, but I have no direction. It's like modern student dilemma. It's like, my function is defined, but I don't have a limit. I'm not differentiable. So the first thing, the function is not differentiable. Remember, for differentiability, we need limits as h goes to 0 of f of c plus h minus f of c all over h exists. Essentially, this means we can do the derivative calculation. The first 4 points we get for free, because we have stated that the function is discontinuous at 1, 2, 3, and 4. So we would say that f is not differentiable at 1, 2, 3, 4, 5, and 6. 1, 2, 3, and 4 we get because the function is discontinuous at 1, 2, 3, and 4. So at 1, 2, 3, and 4, the function is discontinuous, so it's not differentiable. That's all you need to say. Because we have previously entered into evidence that the function is discontinuous at 1, 2, 3, and 4, and we have proven our case. At 5 and 6, we observe that there are pointy bits. This limit doesn't exist because the slope coming from one side is different than the slope coming from the other side. So our intuitive explanation for 5 and 6, sharp corners. This was the preferred one everybody used yesterday, so we'll go with sharp corners. Sharp corners will almost always mean that the limit as h goes to 0 from the left is not the same as the limit as h goes to 0 from the right. I didn't want to write the whole expression. But it gets back to our idea about the limit. Are we headed the same place from either side? With differentiability, we're not headed the same place from either side. I wrote delta y over delta x to write less and to remind you that this calculation is about finding the slope of its line tangent to a curve at a given point. How's everybody okay? Is calculus super easy? Is calculus only super easy because I haven't asked any like very direct questions about all the stuff from chapter 1 from pre-calc that you might have forgotten about? Like if I gave a quiz, like, oh, tomorrow's quiz is going to be on trigonometric functions. How many of you be like, oh, I'm going to be sick tomorrow? And then after that, it's going to be on logarithmic functions. Like, oh yeah, I think I've got like a 48-hour bug. And then the day after that, it's like, well, how long do you want me to be sick for? When are you going to stop trying to give us tests from chapter 1? We're going to hopefully take some time as we go through the rest of the semester to find out what we don't know from pre-calc. I can tell because I just look at the results of, let's say, polynomials and powers polynomials and rational functions, and I look for the problems that took everybody like 12 attempts and 40 minutes. It stops at 12 attempts because what happens after 12 attempts? Has anybody found out what happens after 12 attempts? What happens after 12 attempts? I give you the answer after 12 attempts. The fact that y'all know that means it's easy for me to find out what's missing. You know what I mean? Like, I'm pretty sure everybody understands FOIL, right? What's FOIL stand for? What is it? First, outer, inner, last. Awesome. What's it for? Everybody's like, oh, come on, man. It's just multiplication. Remember when you learned to multiply numbers? It's the same fucking thing. Sometimes, the reason I say that, some of you are like, oh yeah, obviously it's multiplication. But it's not obvious to everybody. So let's say the obvious thing. FOIL is just the same thing that you learned when you first learned to multiply numbers, which is all how multiplication and addition interact with each other. What's it called when we take multiplication and spread it out over addition? What's that called? What's that called? That's a sign language. Distribution. It's the distributive property. Multiplication distributes over addition. We usually say the distributive property, which is bullshit. There's more than one. Exponents distribute over multiplication. So there's multiplication distributes over addition. Exponents distribute over multiplication. All right. So we will find out more what we need to work on from pre-calculus, any gaps in our history, and we will try to fill those up. While we're doing that, continuity, differentiability, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing